All right, are we all good? Thank you very much. Put your hand up if you saw Ruben yesterday. Okay, so repeat crowd, more jokes required. Can't use the same ones. Bit of pressure. What I loved about Ruben's presentation yesterday, he made what I guess we all are aware of in our life suddenly become something that you learn. I never realized that, or I never thought that. And I think this is what this whole sort of way of communication is about. It sparks our curiosity to find out more and then to ask another and then to ask another. And we're going to get something on that, along those lines this morning when we bring the periodic table to life. And as someone who's struggled with science, let me tell you, the idea of talking about periodic table for, 35 minutes, I could struggle, but I think we're in good hands. This guy's really good. Please make him welcome, Ruben.
Thank you. Thank you. Thank you. Thank you. And can I check who here is a primary school teacher? Very good. And who's a high school teacher? Okay, so that means I've got to kind of juggle a little bit for everyone, yeah? So for the primary school teachers, I'm going to assume that you, like most of the primary teachers I speak to, get quite nervous around the periodic table. And I'll show you why that happens to a lot of primary teachers. And for the high school teachers, well, did you know that it's the International Year of the Periodic Table? It's incredible how many people do not know that United Nations declared this year the International Year of the Periodic Table. If you're looking for a really lovely one to get started, go to Ansto. You can print this out for free. I'm going to put all of these little links into a blog post, so you don't have to really scribble down too much if you don't feel like it. You can, but that'll all be on my website this afternoon. And so here's one of the reasons primary school teachers sometimes get a bit nervous. There's all these numbers on the periodic table that are just terrifying, because what do they mean? And do I have to memorise them? First of all, no, you don't have to memorise anything. And let's get started with the periodic table and just remind you what it means. It starts over on the left-hand side. There's a little number at the top. The number 1 tells you that that's the lightest atom in the universe. At number 1, it also tells you that there is 1 proton in the middle of these atoms. I often wear a shirt. I realised I'm not wearing my best prop, which is a shirt with a atomic logo on the front. So I'm used to pointing at my shirt to be able to say, in the middle there are protons, and going around the outside there are electrons. Helium has got 2 protons in its nucleus, and that's what makes it helium. All helium atoms have 2 protons in their nucleus. This is not helium. You probably thought it was when you walked in. This is hydrogen. It's number 1. I'm going to prove the difference between that gas and helium, which I have in this bottle here. And you can now buy it for about $40 in a bottle from Big W or Spotlight. There are so many places that sell it, and you don't have to pay rental on the bottle. You've got to pay $16 a month to keep this. So things are getting better and cheaper and faster. Back to the periodic table for a second. So as you go along, the numbers at the top of each of these symbols tells you how many protons are in the middle, but it also then tells you how heavy they are, and you're going to see why that's so important in a minute. So it goes along, and if you've got, please go back to your classroom if you've never done this and ask your primary students who's seen the periodic table before, and at least one hand will go up. When I was at Matthew Pearce Public School a few months ago, in Western Sydney, I said, hey, we're going to learn about the periodic table today. And half the kids went, yay! And all the teachers went, what? They couldn't believe that their kids knew so much about it. So we sang the periodic table up to, I don't know if you've heard the song, but it goes, there's hydrogen and helium and lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, there's oxygen so you can breathe, and it keeps going. And all these kids sang it with me. And their teachers were like, couldn't believe it. Kids love this thing. So let's get to know it a little bit better. For the high school teachers, do me a favour and be honest, because I've asked so many people, why are those little elements down the bottom there not part of the main table? My friend, no, I won't say because I'm on camera, but the calibre of people who didn't know, including me, why are these elements down here not part of the main table? If you ask children, or a lot of adults, why are those elements not part of the main table? A lot of them will say, oh, are they gases, maybe? And the other ones are not gases. No, that's not it. Do you only find them on other planets, maybe? and not on the Earth? Nope, that's not it. Are they the radioactive elements? No, that's not it. A head of science at a very prestigious private high school on the Gold Coast, when I said, do you know why they're there? Said, oh, aren't they the synthetic elements? That's not it. So get this, and I don't know what I would have said to you 10 years ago, because I did not graduate university with a physics degree knowing the answer to this. How's that for a fact? So these elements fit into that little gap there. If you follow the numbers along, you'll see, oh, okay, you get to barium number 56, and then 57 to 71, what does that mean? Oh, you've got to go down to the lanthanides, and then you get to the end of the lanthanides, lutetium, and then boonk, you've got to go back up to hafnium, which I use to coat laser mirrors. And then you go tantalum, and it's so confusing, this thing. So here's why we don't put those elements there. You're going to laugh your head off if you don't know the answer. Does anyone know the answer for sure? A couple of you know. So look around the room. Maybe 3 or 4% of you knew. So the reason we print it the way that you're seeing it in books is because, well, actually those elements belong there, but if you fit them in, that's how the periodic table's meant to look. But can you see what's just happened? The letters got really small, and now you can't read them very easily. And so to fit it on the page, we just print it the other way, because then the letters don't get so small. It's a printing issue. It's a font size issue. That's it. So every high school should have this on their walls because they've got space. It's A4 paper that doesn't have the space. So let's correct this little problem and make sure kids understand that that's the shape of the periodic table. Now, this is the alphabet of the universe, and let's get deeper into it. So if you take the elements and you line them up like this, and you can do this with a piece of paper. In fact, while that's happening there, I'm going to get mine because I've got it right here in my bag. I take it everywhere I go. This idea of teaching kids about the periodic table by printing it out in one long line, just like you can see it there. When you do that, it looks like a tape measure. And that's the first 92 elements of the periodic table. They're all of the naturally occurring ones. There they are, and you can make that with your kids. It's so easy. I'll make sure you can find the PDF that you can print this out on A4 paper. And then you'll know, you'll start to appreciate what this thing is really telling you. And it just gets better and better. So if you look at the first element, hydrogen, I've got that here, and I've also got the second element, helium. And you know that I've got the seventh element, liquid nitrogen, and I'm not going to do lots of liquid nitrogen demonstrations, but I am going to do 1 or 2. And my favourite is if I get some liquid nitrogen and I pour it over a balloon full of hydrogen. Yesterday you saw, and sorry, can I just triple check? Who wasn't here for my keynote yesterday? Just so I'd only a couple. All right. Well, yesterday we froze my breath. And the first thing you see when you freeze gas, doesn't matter what the gas is, it shrinks. So let's freeze some hydrogen gas and see what happens. Liquid nitrogen's minus 196 degrees Celsius. That's not cold enough to make hydrogen turn into a liquid, but it is cold enough to do this. It is shrinking, just like my breath did yesterday. But this is hydrogen, which wants to float because the atoms are lighter than the atoms in the air around it. But now we're seeing something really interesting. As the balloon shrinks, it stops floating. And when I do this for kids, I'll say, oh, well, you know, hydrogen's made of atoms. And when I started, there was X number of atoms in this balloon, like a million or so. And now the balloon looks smaller. So do you think there's still the same amount of hydrogen in there? And little kids go, nah. But there is exactly the same amount of hydrogen in this balloon. So therefore, well then, do you think maybe did the atoms get smaller? And little kids will say, yeah, maybe the atoms got smaller. It's not what happens. Atoms don't shrink when you make them cold. Did the atoms maybe get heavier because it's not floating anymore? And a lot of kids will say, yeah, well that makes sense because it's not floating anymore. But no, atoms don't get heavier when you cool them down like this. So if I stop pouring liquid nitrogen on, then, well, let's watch what happens. Takes off again, got stuck because of the sealing. It's mesmerising. The same number of atoms are now taking up more room. Let's see if helium does exactly the same thing or not, because that's number 1 on the periodic table, and the reason it floats is because the atoms are lighter. That's the whole reason, and it makes sense when you think of it as atoms surrounded by even more atoms. The problem we have with gases that a lot of people struggle to understand is that air has mass. Easy to say, hard to get your head around. The reason we don't notice the mass of air, this is the best analogy I've ever come up with for kids and adults alike. Just think of a bottle of water filled to the brim. You know it's heavy. But put the lid on and jump in a swimming pool with it and hold it under water. Is it still heavy? No, you don't notice its weight because now it's neutrally buoyant because it's surrounded by the same stuff. Whereas a block of wood feels lighter than the air around you because it's less dense. And a rock or a lump of steel feels heavier than the water around it, so it will sink. And let's see helium now, still much lighter than the air around it. And I've tied a knot already. Got to tie another one because I've got to put a ribbon in. Although I could just about reach it from here, couldn't I? No, not quite. I love letting them go without a ribbon on them because you look at kids' faces. When I do these demos, I've done them so many times, it's fun for me to look at the kids because they're not watching me at all. So I can just stare at them and they don't even realise. And their faces are priceless, right? When you pour liquid nitrogen, second balloon, right? Same looking thing. You can't tell the difference between helium and hydrogen with your eyes. It looks exactly the same. It's invisible. Does exactly the same thing. It's shrinking. And will it do the same thing if I stop pouring liquid nitrogen on? Let's see. Same number of atoms. And the difference is, now that they're warm, the only thing that's changed in this balloon is the speed at which those atoms are zipping around. It's amazing. And helium atoms like to live on their own. It's called a noble gas. They don't like to form bonds with other atoms. So these ones are just bouncing around, single atoms on their own, bouncing off the inside of this balloon. These ones, hydrogen atoms, like to make one bond with any other kind of atom. When you've got hydrogen gas, they've all stuck to each other, and so they form one bond, so two of them get together, and that's it. That's a hydrogen molecule. And there they are. And they're still much lighter than the air around them, so they're floating. So now let's prove that they're very, very different. And the way we're going to prove that is with one of these things. And I'll start with number 1 on the periodic table, which, because it's number 1 on the periodic table, it will do. I might put on, I don't really need to put on my goggles, and if I can't find them, I won't. No, can't find them. They're here somewhere. But it's all right, because it's just a bit of hydrogen. On the count of 3, 1, 2. Science, baby, not what you said. Helium, number 2, won't react with anything. So, no reaction. The helium atoms are still bouncing around on their own. They're still here. They're up at the ceiling now. They're sneaking up through every little spot they can get to, and they're going to rip up into the atmosphere. And eventually they'll mix in with the air around them, and if they get anywhere near the edge of the Earth, they'll get booted out and whip off into space because they can reach the velocity you need to escape the atmosphere. So that's a pretty dramatic difference, yeah? Having one proton in your nucleus makes a very big difference. If you have 2 protons in your nucleus, you're a completely different beast. Now, let's go back to the slideshow, if that's all right. So Number 3 on the periodic table is lithium. And lithium is a soft, shiny metal. And high schools, which high schools here have lithium in their store? A couple of you do. Every primary school kid should get to see lithium in water. It's quite safe. It fizzes when you put it in water, makes hydrogen, and you can do the pop test with hydrogen. Anyway, the point is, lithium is a soft, shiny metal, about the hardness of blue tack, and that's a very, very big difference between being an invisible gas that doesn't react with anything, isn't it? Being a soft, shiny metal. Now, beryllium is a metal, and then boron is a semi-metal or a metalloid, and then carbon, nitrogen, oxygen, you've heard of those gases. Then you get to neon, it's another gas that doesn't react with anything, and straight after it you get sodium, which is another soft, shiny metal, which reacts strongly with water. So that's the same kind of strong transition. Just by adding one more proton from 10 to 11, we go from gas to amazingly reactive metal. And you get it again. You get magnesium, aluminium, metals, silicon, semi-metal, and then chlorine, gas, poisonous. Argon, another metal that won't react with anything, and right next door to it, add one more proton, boom, another soft, shiny metal explodes in water. You do it again. That's a huge difference. You go up further. You go through more metals, then you get a semi-metal, then you get non-metals, then you get bromine, which is a liquid, and then krypton, a gas that won't react with anything. And straight after that, boom, rubidium, soft, shiny metal, explodes when you chuck it in water, and it really explodes. And it happens again as you go up the periodic table. You get to xenon gas after metals, non-metals, semi-metals, non-metals, and then after xenon, cesium, which goes kaboom in water. And one more time, we don't know if francium goes kaboom in water, but we can be pretty sure you can't make enough of it, it's radioactive. So there's never been enough to have a lump of it to chuck into water because it radiates away, breaks into smaller atoms. But can you see there's a pattern here? And this is where the word periodic table comes from. There's a periodic repetition of these chemical properties of the elements. And if you divide the periodic table like this is why it's the year of the periodic table. Dmitri Mendeleev noticed this 150 years ago, and he put these elements into a table and he was looking for patterns. And here's a pattern. There's two, he didn't know this bit. There's 2, 8, 8, 18, 18, 32 elements in each of these periods, and they obey the most beautiful little mathematical equation, 2n squared. If you put 1 into 2n squared, you get 1 squared is 1. 2 times 1 is 2. That's 2 in the first period. If you put 2 in there, 2 squared is 4. 4 times 2 is 8. 8 elements in the second 2 periods. 3 squared is 9 times 2 is 18. 18 in the next 2. And 4 squared is 16 times 2, 32. Why does Mother Nature play this game? That is, it gives scientists goosebumps. The scientists who figured this stuff out were going to work every day as excited as a kid who's going on school camp. Like, this is amazing. And we don't teach it to kids very well. We've got to change it. Now, if you take these 92 elements and if you line them all up to the left, Mendeleev realised if you line them up like that, then silicon here, for instance, is sitting above, if you line them up like that, sitting above titanium. But silicon's a metalloid and titanium is a metal. So they're not lining up nicely above chemicals or elements with similar properties. Whereas so germanium is much more like silicon. It's a metalloid, shiny metal, hit it with a hammer, crumbles into bits. But it still conducts just a tiny bit of electricity. If you line them up like this, now we've got silicon above germanium, and now you're looking at the shape of the periodic table. Here's the synthetic elements, the ones that we have to make in laboratories because they don't exist in nature. But if you can ram another proton into the nucleus of an atom somehow, which we've figured out how to do, then you can make a new element. And we're up to 118. And no one knows if we'll ever get to 119. And the day that happens, keep an eye on the news. There's a Nobel Prize right there for the next person who puts another element in. It's going to really blow chemistry brains out of the water because we don't know if you can do it. Now, you now understand the alphabet of the universe. Everything is made of these things. And you also understand why they are arranged like this. Yesterday, I showed you that if you freeze your breath, you can make the oxygen turn liquid and you can make the carbon dioxide turn solid. Let me show you very quickly the amazing difference between number 7 on the periodic table, which is nitrogen, and number 8 on the periodic table, which is oxygen. And I'm going to put a little bit of liquid nitrogen into a tin, just 1 teaspoon, just to show you one of the hazards of liquid nitrogen. And look, I do a whole hour or 2 hours of safety training for teachers on how to use liquid nitrogen safely. I've been mucking around with it for 27 years, and you can do all sorts of great stuff without hurting yourself. But if you swallow this stuff, then, well, look what happens if you put it in a tin with a tight lid. It pops. So when you do that, kids go, yay, do it again. Sure, let's do it again. Should we put more in? Of course we should. So that's a little bit more. And they get very excited. They think it's going to go higher. Now, in a room with a low ceiling, I can't show you that it doesn't go higher. But I usually put even more in. I almost fill it. It always goes to about the same height. And that's because the thing that's making that lid pop off is the fact that liquid nitrogen is made from air. And to liquefy it, you start with air. Here's an hour's worth of my breathing. So for the people who weren't here yesterday, that's how much air I breathe when I'm asleep in 1 hour. It's 360 litres, and I've separated it into the fact that it's 80% nitrogen, 78, and about 21% oxygen, so 4 out of every 5 molecules in the air, nitrogen. That's where we get liquid nitrogen from. And 1 out of every 5 molecules in the air, oxygen, roughly, right? And so the British Oxygen Company, BOC Gas and Gear, they're called over here, British Oxygen Company makes billions by squashing air, selling the oxygen to hospitals to keep babies alive if they're born prematurely, etc. They sell compressed nitrogen to GPs to burn off your warts and your moles, and industry for countless things. If you squash air and you let it cool down and squash it again, and let it cool down and squash it again, you can liquefy it. That's what's happening at BOC. But then when you have the liquid, it wants to get back to room temperature, thermal equilibrium, and as it warms up, those molecules speed up and they spread out 700 times. So 1 teaspoon of liquid nitrogen, this much, will fill both of my graduated cylinders here. I've got a 1 litre and a 2 litre graduated cylinder. So it'll make that much gas from 1 teaspoon, right? That's a lot of gas, and therefore it pops the lid off. If you get it in your stomach, which has happened, I'll show you a quick picture of a girl for who this really did happen. Her name's Gabby Scanlon, and where are you, Gabby? Here you are. She drank some liquid nitrogen because they put it in a cocktail, and they didn't warn her because they didn't know. The staff weren't trained properly, and so she lost her stomach. And I can send you, in fact, it's open access journal article, the case report from the British Medical Journal, and you can have a look inside her stomach because the doctors took photos as they operated and removed her stomach. So this stuff is not to be trifled with. Don't let kids play with it. And so you never let a kid be a volunteer and actually do anything with it. You don't ever turn your back on them when it's in the room. And as long as you do that, it's totally safe. But when I was at the Southport School a couple of weeks ago, or months ago, a kid said, oh, I went to this place in Chatswood and they made dragon's breath. And my ears went, whoa, dragon's breath. I read a case report of a little kid in Korea who had dragon's breath dessert. That's liquid nitrogen in a cup with little biscuit balls. And those little biscuit balls are like Fruit Loops, sort of, yeah? And the kids eat them. So this is in Chatswood, Sydney. The owner of this place didn't realise that what they're doing here is so dangerous. They're letting kids dig those balls out with a shish kebab skewer so fog comes out your face. And that is almost safe, maybe. I wouldn't ever let a kid do it. So I had to visit that place, and the lady's very nice. She stopped doing it that way. But please don't do anything where kids can get it in their mouth, and then no one will get hurt. That's my little safety briefing. I wanted to freak you out that you never ever let kids play with it, but as long as you don't, this stuff is magic. So, watch this. If we put a teaspoon of liquid nitrogen into an Erlenmeyer flask, it's going to expand 700 times. And as it does, it's going to force whatever air is in there. As it expands, it's going to push that air out. So it's forcing the oxygen out of my little flask. And I've put in 2 just to be certain that it's going to force it all out. Now, in this second flask, I'm going to add some 3% hydrogen peroxide from Coles or Woolies. And you only need a little splash. I found this demo in the Journal of Chemical Education, and I can just picture the teacher who found out that this works, because the other thing you need is bleach. And from also, well, you need bleach from Bunnings, because the other bleach at Coles, Woolies, they add detergent and it's foamy. So this stuff hasn't got the detergent in it, and so you can see all that bubbling going on in there. That just released the oxygen atoms from the hydrogen peroxide, H2O2, and sodium hypochlorite. And now this one is full of oxygen and this is full of nitrogen. And so now I can show you why that's such an incredible difference. So if we get this is the world's oldest test for the presence of oxygen. When Captain Cook sailed past, or into Botany Bay, oxygen had not been discovered. But when the first fleet sailed into Sydney Cove, oxygen had been discovered. And here's how Joseph Priestley and Carl Scheele both discovered it. Here's how they proved they had oxygen and not normal air. If I blow this out and then dip it into just normal air, nothing happens, as you'd expect. But if I dip that glowing splint into pure oxygen, it catches fire again. You do that in front of a bunch of grade 3 kids, and oh my God, they are, whoa! And then if you stick it into nitrogen, they cover their ears. They're not sure what's going to happen. But it just goes out. And if I stick it in here, it comes back on. And if I stick it in there, it goes out. So it's on, off. Happy, sad. Alive, dead. And when I've got this, I like to remind kids that this fire is exactly like you in that it needs oxygen, and without oxygen, it's dead. And so are you. You've got a couple of minutes without oxygen, and then you're dead. And it's because the chemical reactions that are keeping you alive to think about this stuff release energy, and that's how come you're warmer than your surroundings. And without that oxygen, you and I are dead. By the way, this is a lovely, safe little demo, because if you accidentally drop this, looks like petrol, but it's just salty water in there. So if you drop it, nothing happens. And you can pour that down the sink, because it's just bleach and a bit of hydrogen peroxide, and every primary school teacher can do that. So there you go. Without any kind of, dangerous sort of stuff. I mean, you don't let the kids do that demo, obviously, but here's a lovely discovery that we made in Bangkok when I was there at Bangkok Patna School. The teachers, before I came, asked the kids what they wanted to do more of, and then they asked them again after I came, what would you like to see more of in our primary school in science? And the teachers all thought that after I came and blew everything up and had a really fun show, made fog rings, amazing things happened, the oldest tricks in the book. I shouldn't get any credit for any of them because they've been around a lot longer than me. But the teachers thought, oh, well, these kids will want to do all that stuff themselves. But one of the things they really wanted more of was to watch the teacher do stuff to amaze them. So children love listening and watching adults. And you should all know that, I'm sure, that when you start talking to primary school kids about something interesting, they're like that. And if you come in with some amazing tricks, you'll have them like that as often as you want them. And you can use it to do behaviour management. Now, over here, I've got a massive container of, this is dry ice. And my friends at BOC put some tape around it. I bought this morning from Welshpool. And I'm just going to put some into water. This is, again, the oldest trick in the book. If you just put some dry ice into water, it will bubble. And I'll just remind you that what you're looking at here is what fat turns into if you are losing weight, carbon dioxide and water. In fact, glucose, alcohol, ethanol. Anything that's organic, when you burn it, turns into these two things. And if it's got any protein in it, you'll get a little bit of nitrogenous waste as well. So I'll just remind you again that these two substances, when plants take them in, when I'm in Bundaberg doing my demos, I will always go and grab a stalk of sugarcane on my way to the school. And sometimes I have to go out of my way to do that. This morning I just grabbed some leaves off the side of a tree because I want to remind you that these things here can turn these things here into sugar, which I do have, but I don't probably need to remind you what sugar looks like. Sorry, it's a bit hard when you haven't got a prep room. There it is. Not the sugar, these. So this is magic, yeah? This little thing here can do incredible magic, turning a liquid and a gas into a deliciously sweet, solid, crystalline substance that dissolves on your tongue. And then when you eat it, you turn it back into carbon dioxide and water again. When I'm teaching little primary school kids this stuff, yesterday I did the floating sinking cans thing. The other thing I like to do is I bring along some Mentos. They love Mentos, so can I have one? No, you can't, because this is for my demonstration with a human body, which I have here, a model of a human body, which is a pool noodle. It doesn't have arms or legs, but like every human, it's got a hole that runs all the way through it, from your mouth to your bum. And if you stick a Mentos inside a pool noodle, if I now say to the kids, where's the Mentos? Is it inside my human here? And they go, yep. I go, good, but is it in the foam that my person is made of, or is it just rolling around in the hole that goes all the way through my person? And they go, it's just in the hole that runs right through you. Right, same for, if I give you this and you swallow it, you chew it up a bit first, swallow it, it's not in your body yet. If you get in the car straight after you swallowed it and start driving and get car sick and spew it up again, all of it comes back out, right? None of it really went into your body yet. It was just clanging around in the hole that ran right through you. None of this, if you don't vomit, none of this will make it all the way to your backside. None of these atoms, right? Carbon, hydrogen, oxygen. There's no other kind of atom in this Mentos, none. And so if you swallow it, all of it goes into your bloodstream. And then it goes to your cells. Some might go to your liver, might get converted into fat by rearranging the atoms. But ultimately, if you want them to come back out again, you've got to turn them into carbon dioxide and water, and they will come out of the same hole they went into. It's the most counterintuitive fact I've ever learnt. And just to really drive the point home to the kids, I get a chewing gum and I put that in my human body. And if you accidentally swallow chewing gum, which you shouldn't, so you've got to remind kids, don't ever swallow it, it's not good for you, particularly if you do it a lot. If you do swallow it, all of it will pretty much get to your bum, right? Because it's indigestible, which means you can't break it down into small enough molecules that migrate across your intestines and into your blood. And the only thing in food that you are meant to eat that makes it all the way to your bottom is the indigestible fibre in food. That's pretty much all that should make it to your backside. And so when you go for a number 2, what you're looking at, pretty much, it's 75% water, that stuff, and it's 25% solids, and of that 25%, about a third's fibre, about a third's the bacteria that live on that fibre. Roughly a third is stuff that may be a bit of fat, bit of bile. A few things escape digestion sometimes, but mostly it's just the fibres that you couldn't digest. So I might just go back to my slideshow for a second and just show you something really interesting, because yesterday I showed you that people you ask, and hopefully you've tried this now, when you ask people where do the carbon atoms in your breath come from, most people don't even know what you're saying. They literally don't know what you mean. And so please investigate that and get back to me. Maybe let's tweet about it and do things, because they don't know what you're saying. They don't know what CO2 means. So you have to really show it to them, right? So here's how I show it to kids. You're inhaling oxygen, you're exhaling carbon dioxide. That's just a word. We can write a chemical formula for it. O2 means oxygen gas is made of 2 atoms stuck together, because every oxygen atom in the universe can make 2 bonds. They stick together, and if they both make bonds with each other, then you've got a double bond, and you inhale that, but then when you what's happened there? Sorry, I don't want to play that video again. When you exhale, you've now got an extra atom, and this one here, that there is the solution to the global warming crisis, and what's the cause of global warming? And it's also the solution to the obesity epidemic. And about 99.9% of adults don't know what you mean when you say CO2. So can you see we've got a pretty big job ahead of us, but how easy it is? Just show kids this stuff. They lap it up. And so here is the clue that I love giving people is, where do these carbon atoms come from? Carbohydrates is the clue. When I'm working with kids, I'll say carbo stands for carbon atoms, and carbon is the Greek or Latin for coal. And hydrates, what does it mean if you're dehydrated? If you're dehydrated, you need to drink water. And what's the chemical formula for water? H2O. They all know this stuff, but we just never ever teach them how to connect the dots. So here is the world's most important carbohydrate. It's called glucose. It's 24 atoms. It's C6H12O6, yeah? And if you rearrange those atoms into this shape, then that's glucose. Fructose. And fructose stuck to glucose makes sucrose, sugar, the most delicious carbohydrate in the universe for the human tongue. Here is everything you eat. These are all the atoms in the 4 macronutrients. So I won't go into too much detail here, but there's really only 3 simple sugars that are in everything. If you stick glucose to glucose, you get maltose. If you stick glucose to glucose to glucose to glucose, you just keep sticking them together in a big long string, you get starch. If you stick them together in a different way, you get cellulose, and we can't digest it then. But it's still just glucose to glucose to glucose to glucose. If you stick glucose to galactose, you get lactose, the sugar in milk. And every baby ever born can rip those atoms apart again, but once they're stuck together, they don't want to come apart. And if you don't have the enzyme called lactase to be able to break them apart, then you're lactose intolerant. And most adults, except for us white people of certain descent, most adults and all mammals except for humans become lactose intolerant, because you don't need to be able to break those molecules apart, because you're never going to have lactose again once you're weaned. We are freaks of nature. In a good way. It's so simple though when you look at the atoms, right? So those 3 molecules are all made out of carbon, hydrogen and oxygen, and that's all the carbohydrates you're ever going to eat are made of those 3 atoms. Fats, all of the fats in nature are made of the exact same 3 kinds of atoms, rearranged in different shapes, which gives them different chemical properties, and there are the 3 most common fatty acids in nature. Your body is packed full of them. The cheeks of a beautiful 1-year-old baby, big, beautiful, chubby cheeks that you can't help but give a big squeeze, you go, you little beauty, full of that stuff. That's what makes them so beautiful. Fat has got a really bad reputation. Fat makes babies absolutely gorgeous. If we have too much of it, it can make life really difficult, right? So there's nothing wrong with fat. And if you stick 3 fatty acids to glycerol or glycerine, then you get a triglyceride. That's what we store in our fat cells. That's what's in the baby's cheeks. That's what's in your belly. I lost 16 kilos of it 7 years ago, breathed out 84% of those atoms, right? Or 84% of the weight. Protein is fascinating. There's 20 amino acids that make up all of protein. Or there's 20 amino acids that your body has DNA that it codes for. And I could do another whole hour about what that means. Like, who knows what the heck I'm saying when I tell you that your genes encode 20 amino acids. That's the code for life, and coding's big in schools at the moment, but I would hazard a guess that probably 99% of primary school teachers don't know what I'm saying. And that's not your fault at all. Here's 3 amino acids. The thing to notice here is that we've still only got 3 elements plus 2 more. We've still only got carbon, hydrogen, oxygen, and the blue atoms, which every amino acid has got a blue atom in it. It's not really blue, it's nitrogen. It makes them an amino acid. And only 2 of the amino acids have a yellow atom, sulfur. So there's only 2 more atoms, and now we've got all of the macronutrients. These 2 have sulfur. All the rest have, every one of them has nitrogen. These ones you have to eat in your diet. The other ones, you can rearrange the atoms in the ones that you did eat to make the ones that are not coloured blue here. So the blue ones are the essential amino acids. And what I mean by your DNA encodes for this stuff is it's a big long chain of molecules, which really your body reads those. You have enzymes to read that long chain, and there's 4 letters in that alphabet. And 3 of those letters together, like GAG, what the heck am I saying? I'm really just saying what the molecules are in this chain. But your body reads off this code and grabs one of these at a time and sticks it in a chain, and then it grabs another one and sticks it in a chain. I can show you the gene for lactase that you need to make lactose. It's published in 1987. And look, if you understand that you're made of atoms and that you eat them and then you breathe nearly all of them out, what does the world look like when every kid in Australia knows that? And what does the world look like when every kid realises that if you want to lose weight or if you're gaining more weight than you want, it's because you're eating more atoms than you're breathing out. And if you want to lose that weight, the only thing that will possibly work is to eat less atoms in than you breathe out, less carbon atoms. And that's it. And people abuse me for saying, oh, but you're saying eat less, move more, diet and exercise. That doesn't work. There's studies that prove that doesn't work. It's like I'm talking to like a deluded zombie person. Like, what are you saying to me? It's the only thing that does work. In fact, to say things like, yeah, I can't lose weight. I've tried everything, but I just can't lose weight. Well, guess what? To breathe, to speak, you have to exhale air, and that air will always have carbon dioxide in it. So for anyone to tell me that they can't lose weight, they have to lose weight to do it because they're breathing out some carbon atoms. And that sounds like, I'm trying to make fun of people, but I'm trying to say, snap out of it. Come on, you're living in 2019. We can land rovers on the moon, on asteroids, but I can't teach people that that's how you lose weight. So let me quickly show you one last graph here. This is everything you eat in a day. You eat 4.1 kilos of stuff if you're an average Australian. You eat and drink this much stuff. Here's what it's broken down to. Mostly it's water. You drink about 1.4 litres of stuff as plain water or beverages, tea, coffee. There's 600 grams of water in the food you eat. The average Australian eats 250 grams of carbs a day, 70 grams of fat, 95 grams of protein. Haven't put any alcohol in there. Doesn't make a really big difference, to be honest, unless you drink a lot. 1 glass, 1 hour of breathing. What we don't put into the stats, the Australian Bureau of Statistics is where I got all these numbers from, but they don't tell you how much oxygen a person consumes in a day. So here it is, 640 grams worth of oxygen goes into your bloodstream a day, and then you metabolise it all. Well, you don't need to metabolise the water. It just comes out of you again through your breath, through your bladder, through your bowels, and your skin. Here is where all the action is. These are averages here. These numbers for how the water comes out of you depends on the temperature and how much you're exercising. You can lose 2 kilos of water per hour at maximal effort in a very hot environment. So, depends. But these numbers here are where all the action is. You metabolise this stuff, which means you are rearranging the atoms. That's what metabolism means, yeah? Like metamorphosis, but for food. And so 250 grams comes out of your body as water, 33 grams of stuff comes out of your bladder, and 720 grams of carbon dioxide comes out of your lungs. And if you don't breathe out 720 grams of carbon dioxide that day, but you do put in all that stuff, that's how you get heavier. And if you don't put in as much stuff, you'll still pump out about as much as what's on the right-hand side. You'll lose weight if you don't put what's on the left-hand side back in. Simple as. So I'll leave you with this thought that we really, really can teach every single primary school kid this stuff because we're already doing it. But we're only doing it in a school here and a school there. We could do it with everyone. And we literally can change the world. And it's primary school teachers that can really change the world. So let's do it. And on that note, keep smiling, keep breathing. Thank you.